Welcome back to Cloud 42. I'm James. We're continuing a recent theme here on the channel, which is finishing up old projects that have been neglected for a while. Behind me here is my PM935TV knee mill, and you'll remember we installed a 3-axis DRO on it a long time ago. Well, surprise! It's actually a 4-axis DRO, and today we're going to work on getting a scale installed on the quill. The first thing we need to do is disassemble the quill stop assembly so that we can get some dimensions off of the parts. And the first step to doing that is to remove this plug. Throwing it on the floor is optional, but if you do, just make sure you find it. You're going to need that. This is just a little screw that plugs a hole, and behind it there is a small lever that actuates the upper quill stop so that when that button is pressed up, the screw is pushed down. Now to get it out, it is threaded. I'm using an M3 screw here that will just fit in and grab the threads. It's not really correct. I think this is probably a number 6 thread, but an M3 screw will grab it enough to pull it out. You can see it's a little dumbbell-shaped lever. Once that's out, we can remove the pin. And we'll just keep track of that and make sure it goes back in the same direction it came out. Now I'll just screw the stop up here to get it out of the way, and we'll take out the bottom lever. There's just a little threaded pin here that we can back out, and then the bottom lever will drop out. And this is the lever so that when the screw goes down, it pushes up on the release pin. You can see there's a little adjustment on that. We'll make sure not to disturb that. And then the release pin falls out the bottom. I'm just making up the names of these parts. I don't really know what they're called. Then to actually get the screw out, we have to take off a snap ring here. If you lift it up so that the tips of your snap ring pliers can go all the way through, it's a lot easier. It is captive. It won't come off until the screw comes out. And to get it out, we just need to take the stop rings completely off. Now, they don't really have to come completely off to continue disassembling this, so we'll just go ahead and leave it there for now. There is an 8mm hex screw in here that we need to remove. And while I'm winding up this wrench pretty good, it's not coming out, so we will resort to impact. Got my little 3/8 Milwaukee impact here. I usually have this on the lowest torque setting so I don't strip things. We're going to need to go a little higher this time. And that makes short work of that. I'm just looking at the machining on this part, and honestly, it looks like somebody went after this with a dull beaver. It looks like it was fitted maybe with an angle grinder. I don't know. It's kind of a loose fit in the slot here. It appears to be a little bit tapered, so I think somebody just hand fitted this and not in a good way. Well, let's measure the slot so that we know what we need to fit, since measuring the part is not going to bear much fruit since we don't have flat surfaces. I'll just take the stop nuts completely off of this and take the screw out so we have full access to the slot, taking care not to lose the snap ring. And then I'm going to measure the width of the slot using an adjustable parallel. This is a Starrett, but there are many brands available. We'll just put it in the slot and expand it so that it makes contact with both sides, and then tighten the screw. Then this will give us something we can pull out and measure with a micrometer. Just slide this up and down and make sure the fit is the same from top to bottom. There is a little paint on this slot. I'm probably not going to mess around. I'll probably just leave it the way it is. This seems like a pretty good fit, and we'll measure and see what we've got. Looks like the slot is about 623 thousandths. That makes sense. This is probably 625, is probably 5/8 with some paint on it. Just out of curiosity, let's measure the stop and see what it is. And unfortunately, this is tapered, so it's kind of hard to tell, but it looks like it's probably 621, 622, something like that. You can see this thing is not something that we can really get a good measurement off of, so we'll go ahead and make our new part to fit into the slot on the mill as we measured it. Now, there actually was a replacement quill stop that has screw holes on top for mounting the reed head of the scale that came with the kit, but every dimension of this is wrong. We could machine this down, we could machine out all the holes, we could make it narrower, but in the end, it's still aluminum, and the aluminum is going to wear quickly against the sides of this slot, and I really don't want to go that route. I'd rather just make a new one out of steel, so that's what we're going to do. Got a piece of mild steel here that I just cut from a bar over at the bandsaw. Now you've seen me and 100 other YouTubers square up stock, so we won't spend too much time on this. We'll just tap it down, touch off with a 1/2-inch carbide end mill, move over, and then raise the knee for half of the material that we need to remove. And then we'll just plow it out. No need to measure at this point. I know the rough dimension of the stock. I know what I'm shooting for. I'll just take half off of each side. That's generally a good practice with cold finish steel, just because there are stresses in the skin and you want to take the material off evenly so that those stresses don't build up and cause the part to bend or warp. It's not a big deal on a part like this, but on a long, thin one, it can matter a great deal. Now just pull this out of the vise, deburr the edges over with my NSK pencil grinder, and then put it back in machine side down. And normally you want to put the first machine side against the fixed jaw, but in a part this shape, I can get away with just snapping it down with my little Randy Richard knocker right on the parallels, and it will be fine. Now I'm taking about 10 thou less than I think I need to. I'm leaving 10 thou on here, or 1/4 of a millimeter. I'll take a measurement, and then I'll take the rest. Otherwise, if I tried to take it all in the first pass, I would be depending on the dimension of the raw stock, which is not something I can rely on. Even if you measure it, it may not be parallel. I always measure after the last cut just to see how close I got so that I can learn from the small errors I make on unimportant parts, so that in the future, if it's really important, I can hit my dimension based on the body of knowledge I built up about how my machines behave. Now I've machined the thin sides. Now for the ends, I'm just going to stand it up in the vise and use a square to align it. I could, put this in the edge of the vise and side mill the end, but I'd have to get a different end mill so that I wouldn't leave ridges on it. And with a small part like this, this is just as easy. Measure the final dimension, and that part is square. Just need to deburr it, and we're ready for the next step. There are a bunch of different ways we could machine the boss on the end of this part. We could do it with a rotary table in the mill, but I'm going to do it in the four-jaw in the lathe. This seems simpler, and it also sets me up better for some of the boring operations I need to do after this. Now, centering up a square rectangular part in the four-jaw is, in theory, just as easy as a round part, except that you have to take measurements on both sides and then pull back the dial indicator while you rotate the part around to check the other side. In practice, it ends up being quite a bit more complicated, particularly because it's very easy to be off by one full turn of the dial. So make sure when you do this, you are looking at the small hand on the dial indicator to make sure you didn't get bit by that. I may or may not have wasted a bunch of time dialing this part in, because I did exactly that. So once we've got the long dimension dialed in, we'll go ahead and do the short dimension here and just keep working back and forth until we get this right. You can see as I take each measurement, I'm rocking the chuck back and forth, trying to find the minimum. Sometimes it's easier if you just put the chuck key in and use that to rock the chuck. So once I get the short side done, I go back to the long side and just keep working it until it's centered. Now that we're pretty close, I'll take the dial indicator and put it on the face and just check to make sure that it did align squarely in the jaws. And unfortunately, it's not even close. Over 1.25 inches here, we're out by several thou. So I'll just tap that. And unfortunately, especially with those copper pads in the jaws, it is stuck so tight, it is just not going to move. So unfortunately, I have to loosen the jaws so that I can tap it around and at least get the face square, which is probably something I should have done up front, but I didn't. So now I get to go back and measure the sides and dial it in again. Fortunately, it was pretty quick to get this dialed in, and it stayed square this time. So once I got it dialed in on the long and the short faces, we were good to go. Now this is going to be a pretty wicked interrupted cut, so this should be a good test of the new multi-fix tool post. Got a 1/2 inch tool in here with a CCGT. It's a ground edge insert, and we'll see what it does. I just touched off on the end and zeroed the DRO, and I've come in close to my dimension. I'm just going to put a mark here, though on the rectangular part you can't really see it. And we'll just start taking some passes. I'm going to start out really light here. This is, 5 thou per side, so 10 thou off the diameter because I'm not really sure how it's going to react. That seems pretty stable. Seems to be running pretty smooth. So we'll go ahead and increase that. Take 10 per side, 20 thou off the diameter. So this is 0.5 millimeter total cut. And that's working great. So we'll just keep going and just keep working it up and taking a heavier and heavier load and just see how this thing behaves. And I got to say, I am loving the way this thing is behaving. At this point, with the previous tool post I had on here with the compound, there would have been a bunch of flexing, and this thing is just solid. We finally worked up to taking 1.5 millimeters off the diameter, 60 thou total, and this thing is just rock solid. I can actually feel the spring in the lead screw pushing back and bouncing as it enters and leaves the cut, and the tool post is going nowhere. So we'll just keep whittling this down until we get close to our dimension, then start taking some measurements and try to clean it up at the target. We're past the interrupted cuts now, and of course I'm taking such a light cut here that it's not really breaking the chip. We'll just take in the last 5 thou or so, wind it back out to clean up the face, and this machining operation should be done. And we're looking for a final dimension here of 739 thou. Let's see where we ended up. And we're a little bit under 740. I will take that. And then the shoulder length here should be 475. It looks like we hit that pretty much dead on. I'm happy with that. As long as we've got the part set up in the lathe, we'll just go ahead and use it to punch the hole through it. I always try to start holes like this with a spotting drill. This is a 120-degree spotting drill. I find that works pretty well for most situations, and then I'll come back in with the pilot drill and just push it through. This is a 135-degree split point drill, so it enters the steel and goes through easily. These things work great on a small, low-power lathe. Once that hole is punched all the way through, we'll come back with our finish drill. Now, this is not quite the size we're looking for. This is a little bit undersized, and you can see exactly why. These drills tend to wander a little bit. It is wobbling, so this hole is going to be close to the right size, but not exactly on position. So I will come back with a small high-speed steel boring bar. This is a little Criterion pre-ground bar, and push this through in a couple of passes and bring this out to the final dimension. I try to bore on operations like this and not just drill, just so that the hole will be precisely in the correct position. Probably doesn't matter that much in this application, but I like to do it anyway, again, so that I can learn how my machine responds, so that when it does matter, I can hit it. Looks like we're at about 386 thou. We need to open that up a little bit more. I'll just dial that into the DRO and then work my way out, splitting the final cut so that we arrive on dimension. This should be 405 thou. Let's see where we ended up. And it looks like we're a few tenths under. Maybe 3/10 under. That's pretty good. I'll take it. For just a blind boring operation using the DRO, I can handle that kind of precision. Come back with some of my Noga deburring tools and put a little chamfer on the inside and a little chamfer on the outside. Slow it down so we can make the chamfer a little bigger on the outside without shattering, and that looks pretty good. Now we'll flip it around and dial it back in. This always makes me sick because I spent so much time dialing it in the first time, and now I have to take it out of the chuck and do it again. You just want to be really, really sure you have completed all of the operations that are required, because you don't want to have to dial something like this in more times than is necessary. With it dialed in, we can bore out the counterbore. We'll just use the same boring bar and take this down to depth. Now I'm going to do the same thing I did when I was churning up to the shoulder, and I'm going to stop about 5 thou shy of where I actually want the shoulder to be, so I can leave some material on the shoulder in the back to come back and clean up later. Otherwise, you'll see all the marks from the multiple passes in the surface, and I would like it to be nice and smooth to provide bearing for the screw head. Let's take a measurement and see where we are. We're just under 500 thou, just under 1/2 inch, and we're headed for 570. So we'll just take a few more passes here and work our way up to the target dimension. I really do like the way these high-speed steel boring bars cut in mild steel. They leave a nice finish and they cut very smoothly. Now that we've got it out to, I think, the final diameter, I wound it into the center, went to the final depth, and I'm working my way out facing the bottom of the hole. And as I'm bringing it out, I'm watching the DRO and bringing it just to the final dimension so that we don't overcut and leave a groove. Having a DRO makes an operation like this a lot easier. That's the dimension, so we'll back it off, pull it out, and see where we ended up. Blow the chips and oil out of here so we can get a good measurement, and you can see that boring bar leaves a nice finish in the hole, and it leaves a nice smooth finish when you back face it on the bottom. I like that. Okay, let's see what we hit. It's supposed to be 570, and we are at 569.7, 3/10 undersize. Does this matter? Not at all. But again, I always try to hit the dimensions as close as I can, just so that I can learn. Deburr the edge here. It's a little big for the countersink, so we'll just use a standard deburring tool. And that should be all of the lathe operations on this part. I think everything else is going to happen over at the mill. I've got the part set up on its side here in the mill on a couple of parallels, and I'm just using an edge finder to find the center using the half function on the DRO and the end. And that'll allow me to use the DRO to locate the position of the clearance hole for the stop screw. Now, to actually knock the bulk of the material out, I'm going to use a Rotobroach or an annular cutter. This is an R8 arbor that goes in the mill and holds the two Weldon flat 3/4 inch cutters. And we'll just get plenty of oil and just push it through the part. This is a little smaller than the hole we want. And because of the way the annular cutter works, it's going to leave a core that's going to pop out. And there's the sound of it popping out. Now it's sitting in the bottom of that hole. I don't want to try to drill into it, so I'll push that out of the way and then finish making the hole. And you hear the second slug click out of the bottom, just like that. And now we have a hole through the part. Now to bring this thing to final size, I'm going to use a boring head. This is a Chinese clone of a Criterion boring head. And I'm going to use that same high-speed steel boring bar I was using in the lathe. We'll set it up, and I'm just kind of rocking it back and forth and trying to feel for it to make contact with the surface so that I can get a 0. And then I will just dial in the amount we want for the cut and take a pass. I'm using the auto down feed here on the mill, so we'll just engage it and let it run. This is an interrupted cut, but so far it seems to be behaving itself. I have the stop set, and I did reinstall everything that we removed back at the beginning of this video so I could perform these operations, and I'll take it all out again later. Just check with calipers to see where we are. This does not have to be precise. It just has to be big enough so the inside jaws of the calipers should be fine. Just take a few more passes here and try to bring this out close to the final dimension. This is a little heavier cut, and you can't hear it as well in the video, but I do not like the way that sounds with the interrupted cut and that springy bar. It was banging around a lot. So we'll back it off and take this in a series of smaller cuts. Engage the feed again. And yeah, that sounds better. Maybe could slow this down. It is making a lot of smoke, but in general, it's cutting okay. Slow it down a little here for the final pass. And this should be very close to final dimension if we're not at final dimension. And once we're through, I am not going to retract it because I don't want a spiral scratch. I will stop it, rotate it around to a point where it won't be noticeable, and I'll raise it up, and that'll leave one small scratch in the bore. Take a measurement with the telescoping bore gauge, and this is supposed to be 765 thou. Looks like we're about 2.5 thou over. That is fine. This is a clearance hole for the screw. To put the threaded holes in the top of the part, I'll just stand it up here on a 1/4 inch parallel and see how well it squares itself up. I wasn't sure how this was going to work, but it turns out it's pretty close. I'm getting down and looking across that square, and I can see no light to the side of the part. So let's put in a drill chuck and get started. We'll start out by just using an edge finder to find the center of the part. I'm using the half function in the DRO so that we can dial to the center, and then I'm doing the whole pattern as distances in X and Y from the center. As usual, I'll start with a 120-degree spotting drill and just get some spots for the drill to start. We'll come in for the tap drill for M4. I know, all the dimensions were in thousands and I'm putting in metric threads. Don't you love it? Tell me all about it down in the comments. Now I am going to push these holes all the way through the part. You remember I've got the boss on the bottom on top of the parallel, so I'm not at risk of hitting the parallel. But I want the hole to go all the way through because I'm going to power tap these with a spiral point tap, and I need some place for the chips to go. So I'll just dial to my dimensions and put 4 holes all the way through the part. And this little, again, it's 135-degree split point drill, does a beautiful job. Now that we've got the holes through, I will bring in the tap. This is an M4 by 0.7 spiral point tap, also called a gun tap. I'll run it nice and slow, and I'll drop it into the hole. I'll give it a little push with the quill so I get a good bite and don't chew up the first couple of threads. And we'll just let it run down to kind of its maximum depth. Again, because this is a spiral point tap, it is pushing the chips ahead of it, and I really can go as deep as I want as long as there's a hole below it for the chips to flow into. A spiral flute tap this small after a certain depth will start to jam up, but the spiral point can go, to its full depth in one pass. Just deburr the top here with my little Noga rotary countersink, and blow the holes out with a little compressed air. Then when I pull this part out of the vise, you can see exactly where the chips went. They just got pushed right out the bottom of the hole where they won't bother anyone. Now the last operation we need to do on this part is to cut the flats. So I will flip it over, set it up on a parallel, and we'll tap it down. But since this is a finished surface, we'll use the nylon end of the knocker. Get that down, make sure that the parallel is tight. This time we only need to center up on X because we have no features to cut that depend on Y coordinates. We are still centered on Y though, so I can just drive to 0, 0 and run the edge finder down into the part as a sanity check. We do not want to scrap this part now. We've got way too much work in it. Now I'm bringing a different end mill. This is a 4 flute carbide finishing end mill. It should leave a nice smooth finish on it. I will just touch off on the part, then lower the knee, and then bring the knee back up to within a couple thousandths of an inch of the touch-off point. I want to only cut with the side of the end mill. I don't want to cut the floor here with the end of the end mill at the same time. I'd like to leave that completely untouched, and a couple thou shelf will not matter to this part, and it won't be visible at all. So I'm just using the DRO, and I'm dialing the same distance on each side, and I'm just establishing a little bit of a flat here that I can measure. Just take an initial measurement with the micrometer and just see where we are, and then I will split what needs to be taken for the remainder between 2 equal cuts, the same as you would do for the final 2 passes on a lathe. Just to try to account for any spring in the machine. There's not really much here, but just in case, I want to be as accurate as I can. Take one more measurement and dial in the remainder and take one final cut. I'm trying to crank this nice and smooth so I get a nice clean cut. And this end mill, this is a Lakeshore carbide 1/2 inch end mill, and it is just doing a beautiful job. Let's blow the chips out and see where we ended up. This is supposed to be 621 thousandths. If it's just a shade under that, it's fine. This is to fit in the groove on the front of the mill. And the micrometer says... looks like we're just under 621, maybe 5/10 under. For a milling operation, especially a side milling operation, that is great. That'll work just fine. Let's pull this out and look at what the surface finish looks like, because these are going to be sliding surfaces. And those look pretty clean. I think that's going to work great. There are lots of ways to deburr parts. You can use a small file. Some people use needle files. You can use stones. You can use swivel deburring tools. There's lots of little tools you can use, but for anything with lots of little intricate details like this, I really like a pencil grinder. This is an NSK pencil grinder. I've got this running at 40,000 RPM, and I'm running a pointed carbide burr. And this just gives a lot of control. Makes it really easy to just dust a burr off an edge, or you can kind of rotate the part in your hand and take passes of multiple angles to kind of round it, or you can take a little deeper cut or multiple passes and leave a nice clean chamfer. You have a lot of control, and that's what I really like about it. It is possible to dig in and cause problems, so it does take a little bit of practice, but once you sort of develop your touch, you can get really good results. Now, if I really wanted to shine this up, I'd take it over and use a stone to smooth that out further, but for this application, that is going to be just fine. Now, I don't normally finish parts like this because nothing rusts where I live, but today I'm going to make an exception. This is going to sit right on the front of my mill, and I would like it to look good. So I've got a bottle of Brownell's Oxpho-Blue, and I'm going to give this a shot. First step is going to be to wipe down the part with acetone. Now, actually, I already scrubbed this part down in the kitchen sink with dish soap to try to remove as much oil as possible, so the acetone wipe is just to remove any residual that might be left. And I know my fingers might be leaving more oil on it, but the instructions actually say you don't have to remove all the oil, but yeah, I'm going to remove it all anyway. I'll just use an applicator swab to apply this to the part, and this is one of the most satisfying things I've done in my shop in a long time. Just wiping this on and watching the steel turn black is it's just fascinating. I could just sit and watch this all day. Now, as I go and as I use up the material in the swab, it's not quite as dark black. And you can see now that I'm getting to this side, it's more or less depleted. So I'll get some more solution. And yeah, replenishing the solution in the swab cleans it up and it gets a lot darker, a lot quicker. So it looks like the key here is just to keep fresh solution on the swab while we work the part. We'll just cover all of the surfaces and try not to miss anything. That is looking pretty good. I'm just going back over any areas that look a little bit light. Looks good to me. So I'll just bring in some tap water and we'll just rinse this off. And I'm just trying to get the chemical off of it and stop the process. I don't think there's any magic to this. Just trying to get it rinsed clean. That looks pretty good. And I'll just blow this off with a little compressed air. With that dry, you can see it's a little more brown than it is black, so we will oil it. And the oil is what really forms the durable finish. The black or brown coating on there just roughs up the surface so that it can absorb the oil. And you can see as soon as the oil goes on, it just turns black. This is just ISO 32 spindle oil. It's just what I happen to have sitting around in a can. I really think just about anything will work. Now I can do this safely because I deburred it and I know that there aren't any sharp edges on it. Use a brush to get it down in all of the surfaces and wipe it off with a paper towel. And this is the finished result. That actually looks really nice. Okay, I might start bluing things more. You can't see the tool marks, though I really don't think it's very distracting. I think it still looks pretty good. If I had a surface grinder, I could clean that up nice and pretty, and I'll bet the blue would look gorgeous then. Let's install this thing and see if it fits. Now, I've already re-disassembled the mill back to the point it was before I put it back together so I could use it. This seems to fit in the slot. We'll go ahead. Okay, who left the autofocus on the camera? Get that screwed in and see, it does seem to clear everything. It does seem to clear the screw, except the quill's hitting the table or the vice jaw. So that looks pretty good. It's not quite level. Let me just sort of tweak it a little bit here with the Knipex pliers. I'll hold it in position and we'll snug down that screw with the impact. I'm not really measuring this, but it's close enough for now. We can fine tune it later. Okay, maybe it's not close enough, but it'll be fine. We can fine tune it later. Okay, the motion seems pretty good. It seems to be moving freely. It seems to be clearing the screw. I think we can go ahead and install the rest of this. Put the release pin in here and the lower trip lever. It's a little bit fiddly to get this all back together. You kind of have to work it in here and feel around until you can get the pin in the hole. Then we'll just snug that down. That seems to move freely. We'll reinstall the snap ring now that we have the screw back in position. Pushing the screw up so that you don't have to manipulate the snap ring right against the flat surface helps a lot. Now we can put in the top release pin and the little barbell shaped lever, whatever it's officially called. Just kind of work it in there till it's in position and then take out the screw. Dropping it on the floor is optional, but if you ever want to take this apart again, you'll need that, so you better go find it. And we'll just go ahead and put the plug in, and that should be that. This is about the third time I've reassembled it, and it's getting easier every time. Let's test the trip and make sure that this still works. We'll just go ahead and manually feed this down until the stop hits. And that works. Let's see if the upward trip works. Do the same thing. And yep, it works. I think if that block were a little bit more level, it would trip just a little bit earlier, and we'll address that in the final installation. This looks pretty good. The last thing I want to check is if we go all the way to the bottom. We can't go all the way to the bottom because we're hitting the vise. Here, you're going for a ride on the table. And now we can go all the way to the bottom. Yeah, seems pretty clean. Doesn't seem to be scraping. I think this is going to work. Now, just in case it wasn't abundantly clear, the whole point of this exercise was to get these threaded holes so that we can mount parts of the DRO to it. I think this is going to work. That was by far the most complicated part of this whole project. Now that that's done, all we need is the bracketry to mount the scale and the reed head, and we're going to do that without drilling any holes in the machine or losing any of the existing functionality. Now, this is where most content creators would tell you to subscribe to the channel so you don't miss that. If you enjoyed this video or found it useful, give it a thumbs up, leave me a comment, and maybe consider supporting the channel on Patreon. Patrons can download drawings and files for all of my projects, including this one. Thank you for watching.